Okay. Done. So good evening, everybody. Thank you, Yuri, for the introduction. Today, I would like to briefly discuss with you a part of my PhD work that I carried on in the last 3 years at Politecnico. That is the theoretical study of how electronic properties of phonon-mediated superconductors can be controlled and modified by field effect doping. Now, first of all, I will discuss what is field effect doping, and then also I will talk about the theoretical and computational technique that I use in my research, as well as the ab-initio implementation of the field effect architecture in this technique. And I will also briefly recap the physical principles behind phonon-mediated superconductivity. And finally, I will discuss 2 case studies. I will discuss an insulator, in particular diamond thin films, and a metal, niobium nitride thin films. Now, we are interested in finding a way to control correlated phases of matter without the inclusion of other chemical species inside our system. This can be achieved via field effect doping, which consists in the modulation of the conducting properties of a material by means of a transverse electric field, which can induce charges in the first few layers of a material. The experimental setup is that of a field effect transistor. We have a metallic gate through which we can apply, we can tune an electric field via gate voltage, a dielectric, and the system under study. Moreover, if instead of a solid dielectric we use a liquid or a gel electrolyte, we can exploit the formation of an EDL, an electric double layer, at the interface between the electrolyte and the material, which acts as a nanocapacitor. Therefore, the electric field becomes very high in magnitude, and we can achieve induced charges which are 1 or 2 order of magnitudes higher than solid-state dielectric devices. Now, how can we study electronic and vibrational properties of materials? Well, in the case of a solid, the usual quantum mechanical approach of solving the Schrödinger equation and finding eigenvalues and eigenvector becomes very complicated and unfeasible due to the huge number of electrons present in a solid and due to correlation between electrons. However, density functional theory allows us to overcome this issue by writing an energy functional in terms of the electronic density. And moreover, in the Kohn-Sham approximation, we map the difficult many-body interacting problem into a simpler non-interacting one, where all the difficult many-body interaction are put inside an ad hoc functional, which is called exchange correlation functional, which is chosen depending on the material and on what we have to simulate. After that, we just need to solve the Kohn-Sham equations in a self-consistent way in order to reach the minimum of this energy functional and retrieve the ground state electronic density, from which we can extrapolate the equilibrium properties of our system. Moreover, this technique is called ab-initio because the only ingredients that we need are the crystallographic and chemical information of our system, of the elements that compose the material. Now, usually, the theoretical simulation of field effect doping has been accomplished by uniformly spread charges inside the system. However, this is not what physically happens, since the induced charge is not homogeneously spread inside the system, and because in this way we cannot simulate the sudden drop voltage at the interface between the system and the gate structure. And moreover, we cannot have the asymmetry given by the field effect transistor architecture. Therefore, recently, a model has been implemented in Dept codes, which treat the ionic layer or the metallic gate as a uniform planar distribution of charges. The dielectric is completely removed and a potential barrier is inserted in order to avoid charge spilling from the system into vacuum. And finally, if we work with a plane wave implementation of Dept, the system is periodically repeated in all the directions. So in order to simulate a surface, we need to insert vacuum between different repetition of the system in order to break the periodicity along one direction, for example, the one perpendicular to the surface. Therefore, the Coulomb interaction is also truncated in order to avoid spurious interaction with periodically repeated images along the non-periodic direction. Now, we know that in normal material, normal metals, the resistivity decreases as we decrease temperature until it reaches a constant value. However, in a superconductor, the resistivity decreases until it reaches a critical temperature where the resistivity suddenly drops to zero. Therefore, superconductor, for example, can be exploited in order to reduce energy losses, for example. Moreover, in phonon-mediated superconductor, we have an interaction between electrons. Here in this GIF, they are blue dots, the blue spheres, which interact with the underlying vibrating lattice, here the red dots. Now, the normal modes of the vibrating lattice are called phonons, and two electrons can exchange a phonon in order to form what is called the Cooper pair. Now, the Cooper pair has an extension which can be very large with respect to atomic distances, and this is called coherence length, which is nowadays exploited for circuits for quantum computers, for example. Now, as a first example, I would like to discuss diamond. Now, why diamond? Because in 2004, it was shown that if we dope the bulk diamond with boron, then we can achieve first an insulator-to-metal phase transition, and then a superconductive phase transition with a critical temperature of around 4 Kelvin. However, even if theoretical predictions suggest that this critical temperature can be enhanced, can be raised by incrementing the amount of boron inside diamond, there is a solubility limit due to the amount of boron that we can incorporate chemically into the closely packed structure of diamond. Therefore, we ask ourselves, can we dope it via field effect and still achieve a superconductive phase transition? We tried to answer this question in diamond thin films along the 111 direction, more specifically in these two papers. And why we chose the 111 direction? Because it is the one that, in principle, should be able to to accumulate more charge as possible with respect to the other two. Now, we have studied 3 doping regimes: low, medium, and high. Let's start with the low doping. Here I'm showing you the electronic band structure in reciprocal space. The black line is the dispersion of the surface, while the gray shaded region are the bulk projected over the surface. Therefore, we can say that we have electronic states at the Fermi level, here the blue line, if the black line falls inside the gray shaded region. Otherwise, it is called surface-like states. Now, we can clearly see that the black line falls inside the gray shaded region. Therefore, at low doping, the system acts as bulk-like. And this is also confirmed by the induced charge density. Here, negative oscillation correspond to accumulation of holes. Indeed, we are studying hole doping of our system. And we can see that the induced charge density spreads well inside the system. Indeed, the 75-80% of the total induced charge density is reached around the 4/5 atomic layer. Indeed, if we also look at how much each carbon layer contributes to the electronic states at the Fermi level, we can see that the highest contribution comes from the 3rd atomic layer, therefore meaning that the system actually is mapped into a bulk, okay? Now, if we move into to medium dopings, we can see that this time the electronic band structure at the Fermi level is outside the gray shaded region. Therefore, we have a surface-like system, and the electronic fluctuations of the induced charge density indeed starts to be very close to the surface layers, and 75% is reached around the 3rd, 4th carbon layer. Indeed, this time, the highest contribution is not very clear to some atomic layer. Indeed, we have a sort of equivalent contribution from all the first three carbon layers, meaning that we are moving towards a perfect surface-like system. Finally, at high dopings, the system again is completely surface-like. The charge fluctuations are strongly localized around the first two carbon layers, and indeed the highest contribution at the Fermi level comes from the first and the second, while the third is just 1/2 with respect to the other two. However, superconductive phase transition couldn't be located for low and medium dopings, but only for high dopings. Indeed, what we predicted was that at high dopings, the system could achieve a critical temperature of 40 Kelvin. However, what's the problem? This could not be seen experimentally. Indeed, up to now, the technique that we have allows us to probe the low and medium doping regime. So maybe in the future, it will be possible also to probe high doping regime and to see if actually we could achieve 40 Kelvin of superconductive phase transition. As a next case study, I would like to discuss niobium nitride, which is a conventional superconductor with a bulk critical temperature of 16 Kelvin. Now, what we can see is that if we apply a field effect doping, if we dope the system via field effect, as discussed before, we can achieve shifting of the critical temperature, which are reversible. Indeed, we have suppression or enhancements of the critical temperature depending if we dope the system with electrons or holes. Now, you have to think that we are doping just the first few layers of our system, okay? So what we measure, however, is a bulk property. Therefore, the first few layers of our material are affecting the whole bulk of the system, and this is called superconductive proximity effect. Now, the depth, the penetration depth of the electric field should correspond approximately to 1 angstrom according to Thomas Fermi theory of screening. However, in a precedent work, they have fitted the experimental results, and they've shown that for low doping regime, indeed, the penetration depth of the electric field satisfies the Thomas Fermi theory. However, it increases if we go to higher induced charge density, meaning that we are breaking Thomas Fermi approximation of screening. So we have tackled this problem from a density functional point of view. Here I'm showing you the total density, the total electronic density, and here the induced charge density as a function of doping. Moreover, we have the same thing here for color maps along a slice of our system. And you can see that if we increase the doping, the fluctuation at the beginning, they are just localized around the first layer, the first two layers actually, which is more or less 1 angstrom, therefore satisfying Thomas Fermi theory. However, when we go to higher doping regime, the charge penetrates inside the system, breaking Thomas Fermi approximation. Indeed, this is caused by a sort of polarization of atomic orbitals. So we have tried to give to compare the experimental results here, the black dots, with a nonlinear Thomas Fermi model and with DFT results. We can see that the nonlinear Thomas Fermi results actually can be used for moderate medium doping regime. However, when we go to high doping regime, the nonlinear Thomas Fermi breaks. On the other hand, DFT results qualitatively well describe the behavior, the trend of experimental results. Therefore, we can see that there is an anomalous screening of niobium nitride and in, let's say, in conventional superconductors, phonon-mediated superconductors, that goes beyond the Thomas Fermi approximation. So, in conclusion, we have seen that ab-initio techniques such as density functional theory allows us to predict electronic properties of materials. Thanks to field effect doping, we can modify the conducting properties of a sample without the inclusion of external dopants. And finally, computational models let us simulate what happens in field effect transistor architecture in great details. As a finish, I would like to acknowledge the people that have helped me during the PhD, in particular, Professor Renato Gonnelli, Professor Davide Romanin, Professor Giovanni Marino, and Dr. Eri Piatti from Politecnico di Torino, who are expert in the experimental measurements of transport properties of superconductors in field effect geometry, and Professor Matteo Calandra from University of Trento, who have helped me during the PhD for what concerned the theoretical part. And I would like to thank you for your attention. If you are interested in more application of DFT in material science, you can go to my website. Thank you for your attention.
Thank you, Davide, for your very interesting talk. We have, again, a few questions.
Okay.
So the first one is, you said you inserted vacuum in order to break the periodicity of the system. Yeah. Why not to exploit a 2D periodicity?
Because, okay, it depends on the code that you use. Because when you use plane waves, all the theory is based on three-dimensional periodicity of the system. In order to recover 2D periodicity, you have to mimic it. I mean, you create a fake three-dimensional system so that you have vacuum along the Z direction, for example, okay, and while the system is correctly repeated along the X and Y. So it's a sort of computational trick to simulate two-dimensional periodic systems.
Okay. Second question. Which are the technical challenges when probing high doping structures?
From what point of view? Theoretical or experimental? Because theoretical, I don't have, okay, theoretically, I don't have any problem. I mean, theoretically, I can do whatever I want. But if I have to compare myself with experiments, now, Professor Gonnelli and Dr. Eri Piatti, they have tried to do measurements on diamond thin films. The problem lies on, first of all, on the type of electrolyte that you use. So let me go a little bit back. Yeah. Here. So it depends, first of all, on the type of electrolytes. So the better is the electrolyte, the better is, let's say, how charges can move and accumulate. Then there is a second problem, which is an intrinsic problem of the material, which is actually called quantum capacitance. So if you have a sort of capacitor due to the system itself, which is in series with the capacitance of the ideal. So it depends on, let's say, of this quantum capacitance of the material, which reduces the effective capacitance of the system, of the total system, and therefore you know that if I reduce the capacitance, then I reduce the amount of charge that then I can accumulate. So if we can find a way to overcome this issue, then in principle we can achieve higher higher induced charge densities.
Okay. Well, we still have two questions. I move to the last one because I think it's more consistent. Which instrumentation is used to perform experimental measurements? Do you need atomic force or Kelvin probe microscopies?
Well, it depends what you want to do. Atomic force microscopy is used just for probing the topology of your system. I mean, you can also, in principle, atomic force microscopy, you can use it in contact mode or tapping mode for looking at the profiles of your sample. Then you can use it also in in resistive mode in order to see what is the electric resistance at each point. However, if you want to probe to study the transport properties, you see, you just create indeed a field effect transistor. So you also add a source and a drain. You apply transverse voltage along the source and drain contacts, so that the induced charge density, so you are probing just the induced charge density at the surface, and you can actually study the conduction properties of these 2D electron gas.
Okay. Well, we have the last question, which is connected with this answer. Did you characterize the possible transistor electronic properties in terms of current voltage characteristics?
Again, from experimental point of view, right?
Yeah.
I see.
Yeah.
Yes, you can study it. You will have a curve which is current versus resistance or temperature, whatever. Yeah, so you actually what you give is indeed, actually, what you are studying is the voltage as a function of temperature, because you inject a certain current, and you see when, for example, the resistance drops to zero. Okay.
Okay.